In this video, we're going to look at a basic problem in projectile motion, which involves something projecting with an initial velocity that's entirely horizontal. And in this case, we have somebody running towards the end of a cliff, chased by this Pac-Man-like monster with, it's a little difficult to see, but these are gigantic red teeth. So you can understand why this person would be running towards the end of the cliff, and is probably at this very moment, and I'll see if I can draw it in there, looking over his shoulder a little bit there, just checking to see over his shoulder about this monster, and he's not going to see that he's at the end of the cliff, so he's going to run straight off and not try to jump. And the danger for him, of course, is that there are these spiky rocks down at the bottom of this cliff. So the big question that's for us to try to figure out is, does this guy make it past those rocks? And we can just briefly outline the path that he's likely to take. It's going to be starting off horizontal and then becoming gradually more and more vertical. And we're hoping that he winds up somewhere out here, safely away from the rocks. But we won't know until we try to figure it out. Now, one of the things that I've been focusing on the past two videos is the independence of the two directions, the x direction and the y direction. And so what I'm going to do is I'm going to break things up into the horizontal direction and into the vertical direction. So I'll have horizontal and vertical components treated independently from each other. So the first thing is that we'll start off with x equals 0 to start with. And the way that I'm going to approach this is I'm going to look to see where he winds up, which seems like a sensible way to go. The other way to go would be to say, let's just say that he goes 8 meters. How fast would he have to go in order to travel 8 meters? But because we've been given this 5 meters per second, I tend to prefer that way. I think the solution's a little bit more clear-cut. So we have a velocity in the x, which we know is 5 meters per second. And the time, we don't know. We don't know how long he's going to be traveling before he hits the water. We also don't know how far he's going to go before he hits the water. So these are our two unknowns here. And the problem with this is that there's really only one viable equation. I left out a couple of things. I left out an initial and final velocity. I didn't worry so much about them because the velocity horizontally is going to be constant. The net force, I could write it like this, the net force in the x direction is going to be 0. So that means that the acceleration is 0, there's no change in velocity. So really my primary points of interest in the horizontal direction are just these four things. The average velocity, which is constant, the initial and final position, and the time. That means that there's really only one relevant equation, which is going to be velocity in the x equals delta x over time. So this is for my horizontal direction. This is really the only relevant equation. All the other ones have acceleration in it, and our acceleration is 0, so it'll just cancel itself out in all those other equations. The problem, though, is that I have two of the four things here are unknown. We don't know where we wind up. We don't know how long we're going to be moving forward. So we need to find out some more information. And that's when we go to the vertical direction. So in the vertical direction, we start off knowing that the height is 20 meters. By the way, the other alternative would be to say that we know how fast this guy is going. We know how far this guy is going to go. How high up would he need to be? Maybe 18, 20, 25. How high up would he need to be in order to get 8 meters out while going 5 meters per second? So there's really at least three different ways that you could have approached this. I'm going to be looking for this one right here. Where does he wind up? His final position in the y direction is 0 meters. The initial velocity in the y direction, 0 meters per second, because the initial motion is entirely horizontal. The final velocity in the y we're not sure about. This is the velocity that he has just before he hits the water. And the acceleration is going to be due entirely to gravity, so that's going to be negative 9.8 meters per second squared. And then once again we run into this time. We don't know what the time is. And this is really the key for us, because what we're going to do is we're going to take this time, we're going to solve for the time in the vertical direction, and use that time to help us figure out how far he goes. So really the idea is that the height is the determining factor for how long this guy is going to be in the air. And how long he's in the air is going to determine how far he can go, given that he's going to be traveling at 5 meters per second forward for every second he's in the air. So the approach to this one is to recognize that we have everything except for time, which we're going to use. Time is our connection between the two directions. And this final velocity in the y direction. We don't know it, we don't care about it. So what we're going to do instead of worrying about that is just solve for the time. So we have y equals y naught plus v naught in the y direction times t plus 1/2 a t squared. And this problem is easier than a lot of problems because first of all I can make that 0. And this whole term I can make 0 because my initial velocity is 0 in the y direction. So then a little bit of rearranging. Move this over to the other side through subtraction. And then multiply by 2 and divide by the acceleration. And we get negative 2 y naught divided by the acceleration. Square root that to get the time. So we have all the information that we need to get the time. And I'm going to just solve for this real quick. And that's about 2.02 seconds is how long this guy is going to be in the air. And right off the bat, we should probably be able to recognize that he's going to make it. He's going 5 meters per second, 2 seconds in the air. He should be able to clear that just for confirmation purposes. We'll go ahead and we'll solve this out. So the change in position equals the velocity in the x times the time. And that will give us about 10.1 meters is how far he's going to go. So he's going to land. This picture is pretty accurate. He'll land somewhere out here. And you would think that he would be safe with that, but unfortunately there are sharks. There are sharks circling around. So he's still in some danger, but the sharks are fine. That's better than the rocks. The sharks might leave him alone. Now, a couple of the points that I'd like to just reiterate here. We set up our givens and we split them up based on the direction. So horizontal givens, vertical givens. It's absolutely crucial that you do that, because otherwise you're going to be mixing and matching, and you might, for instance, say something silly like there's an acceleration due to gravity of 9.8 meters per second squared horizontally. So you have this person accelerating off the cliff and continuing to go faster and faster sideways as he goes. That's absurd, but people do it. People, when they don't split up their givens into horizontal and vertical directions, mix up things in such a way that they say gravity is acting sideways. It's things like that that don't make any sense at all, where I'm going to take off a lot of points. You make math mistakes, no big deal. But if you start saying gravity is acting sideways, we have a problem. Some other things. One thing that we should do is kind of get a rough estimate of what's going on. If you're dropping 20 meters with an acceleration of about 10 meters per second squared, that should give you a rough idea that it's going to be a couple of seconds of a drop. So you should be aware that this is going to be close. We shouldn't get strange numbers like even 4 seconds would be an awful long time to drop 20 meters. And that's something that happens as well. Sometimes people forget to take the square root, and they just say that instead of solving for time, they're solving for time squared, but they think that they just solve for time. So just please be careful with the setup of the problems, and try to think your way through them a little bit ahead of time to make sure that you know whether your answers are reasonable or not, and to make sure that you're not doing things like having horizontal accelerations due to gravity.